Hi everyone, I'm Onkar.
Hi, I'm Ullas. Today we walk through two research papers that form the foundation of our project and how we plan to replicate and improve upon them.
Let's start with the first paper, Transformer Interpretability Beyond Attention Visualization by Hila Schaefer and colleagues, presented at CVPR in 2021. This paper tackles an important problem. Although transformers, especially vision transformers, are powerful, interpreting their decisions is incredibly challenging. Most previous methods assume that raw attention weights indicate a feature importance, but that's not oversimplification and often misleading. The author proposed a new approach based on layer wise relevance propagation, which is also called as LRP, adapted for transformers. Instead of relying solely on attention, they compute class specific relevance sources that flow backward through entire model, including tricky components like GELU activations, skip connections, and matrix multiplication. This results in high resolution, class discriminative visualizations that outperform the traditional attention maps and GradCamp benchmarks like ImageNet segmentation and the Eraser NLP benchmark.
Exactly. What we are planning to replicate from this paper is the idea of moving beyond raw attention visualization by focusing on relevance scores. In our project, we implemented a lightweight version of this idea using fine-tuned vision transformer VIT and on Cipher dataset, adapting relevance propagation to generate clear class-specific heat maps. Yeah, but we also plan to improve a few steps. Firstly, by integrating RadCam overlays to make the result more user friendly for non-technical audience. Second, by supporting batch-based inference for real-world scalability. And the last one, by conducting robustness checks with noise and perturbation, something that was partially explored in the original works.
Moving on to the second paper, Demoscopy Image Classification based on StyleGAN and DenseNet 201, published in IEEE Access 2021 by Shen Zhao et al. Here, the focus shifts from interpretability to data scarcity, a critical challenge in medical imaging, especially for skin lesion classification. The author proposed a creative framework combining a custom style GAN to synthesize new skin lesion images and DenseNet 201 classifier trained on both real and synthetic data. Their results showed a remarkable 93.64 percentile balance multi-class accuracy on the ISIC 2019 dataset, significantly improving classification performance for rare and malignant lesion types.
And for our project, we are heavily inspired for this idea of synthetic data augmentation. We built DermaGAN, where we used a custom GAN to generate high quality synthetic images and trained a CNN classifier, not DenseNet, but a lighter model optimized for efficiency. But we also introduced some enhancement over the original paper. Our GAN includes skip connection for better feature preservation. We balanced real and synthetic data at different proportions and tuned them throughout the ablation studies, and we evaluated not just overall accuracy but per class precision and recall, especially for underrepresented categories like melanoma.
So, in summary, both papers provided us a powerful ideas, interpretability from the first and data augmentation from the second. But we went a step further by integrating real-world usability features, testing robustness, and tailoring solutions significantly to smaller resource-constrained datasets like CIFAR10 and dermatology images.
We're really excited about how combining transformer relevance propagation with GAN-based data augmentation can push forward both explainability and performance in deep learning models. Thank you for listening, and we look forward to show you the full results of our projects soon.
Thank you.
Thank you.